Hello everyone. So in the last, in the first session of Design Compiler Labs, we saw how to set the libraries. We read in an example RTL file, saw the elaboration report. We studied how we looked into how to report on the library. So today we'll go ahead and compile our design. This design consists of about 8 to 10 files of Verilog. So it's a decent enough design to do your experiments. It even contains memory. I'm not very familiar with the design. It comes from Synopsys. It also has some power controller into it. So let's look into the design first a bit, and then we will read in this design, and we will set the constraints, we will set the environment conditions, and then we will go ahead and compile the design. Now, as a synthesis and timing engineer, it is not necessary that you know complete inside and out of the design. Even without knowing what actually is implemented in there, as an engineer, you could always synthesize the design. So the major things to know are, first of all, the environment conditions, and in most of the cases, the synthesis engineer himself is the one who will decide on that. Plus, obviously, we should know about the some interface, something about the interface to which the block being synthesized connects to, so that we could work the input output delay. Obviously, we should know what are clocks are there in the design, what are the frequencies, and what are the relationships. So just by knowing a few things, we could do the synthesis and then later do a lot of analysis and reporting to make sure that the synthesis is correct. So it is not at all necessary to know each and every part of the design. Since I do not know each and every part of this design, still we will synthesize it, and still we will get some very useful data out of it. Right? So these are the all the .v files listed on my desktop. This all constitutes the design. The top level is top odc.v, and the module name is chip top. So we could see there is a memwrite bus, memwrite valid. There's a clock, the reset signal, there's a power signal. So it looks like some kind of a memory controller, kind of a design, which just by the name it suggests that it's some kind of a memory access thing with some kind of power, some functionality to limit the power. So we see the inputs and the outputs. Let's see what are the instantiations here. So we see that the top level in most of the cases will be a more or less a structural design. So we see there's an instruction decoder. We see there are some general purpose registers. Then there's a multiplier. There's a sign multiplier. So it's good that we have a multiplier. We have a data path here. We have a power controller. There's some address generation logic, and there's a memory memex hierarchy. Now this would be the so there are two instances of there's one memex hierarchy, there is memy hierarchy, and I guess these memex and memy higher blocks contain the actual memory instantiations. We could see that. Let's grep for let's see where is the memory instantiated. So yeah, so memory is instantiated in these blocks. X. So this is the block. Now, see, the interesting thing about this block is that it has some instantiations of buffers. So now the RTL designer, for some reason, chose to instantiate some buffers in this RTL. Now, in this case, this RTL now is not technology independent. Why? Because this is using some buffers from a particular standard cell library. If I want to use this RTL with some other standard cell library from some other provider, I'll have to make sure that these buffers get replaced. So in many cases we want some specific buffers to be in place, so we instantiate them explicitly inside don't touch on them so that DP does not remove it. to reduce area. So there are various reasons why it is done. Sometimes for layout considerations it is done. There can be many reasons. So but we see that there are a lot of buffers here, and I guess they will be set to don't touch later in the future flow. And the number of buffers. So address looks like all the inputs are being buffered and outputs are being buffered. So let's see this input common address. So we see that yes, the common address is being buffered. So this common address int, which is the wire driven by buffer, goes to memory. So it is a very good practice to buffer the inputs to memory and the outputs to memory. Usually what happens that memories, we have to make sure that the transition to the inputs of these memories and from the outputs of these memories are very good. So it's a good practice to have explicit buffers and tell the layout engineer that please make sure that these buffers are placed close to the memory address. So that way you are making sure that the transition numbers are good. Usually memories like this, so this looks like a one port read write memory. So this is a usually the memories like this have high access times and very critical. These are always time critical memories. Either on the input side, the setup and hold windows on the action are very strict, and the access time from the clock to the data out is usually more compared to flip flops since memories are complex projects. So it's always good to maintain good transition numbers at the input and the output. So now we see that there are two instantiations of memory. Now, if you look at the RTL, there is no module definition for this memory. So how does DC know about this? So DC needs to know the module definition for each and every block, right? Each and every instance. It needs to know what is the module definition. Now for this memory, the module definition does not come from the RTL. Since it's not a synthesizable logic. It's a macro that is already being that's already constructed and given to you to be used directly, to be used explicitly. That is why we have a dotlet for it. So yesterday we saw that there is a memory dotlet. So we see that we have a memory dotlet of SRAM, which is this, and in our let's go to the work area, and when we will so I've already started design compiler. So now we have to make sure that this memory, this .db, is part of the link library, not the target library. So what we will do now is we will read in the complete RTL and see what happens. So I'll copy paste some commands. This way you can actually go ahead and make your own script file. So it's a good practice whenever you synthesize a block to make a script file so that you can just source it inside EasyCell. When you want to repeat the process, you don't have to write each and every command every time. So I have a script file. I'll just copy and paste stuff from this. So we'll just review these steps. I'll set the search path, the link library, target library, and the defined design list before sourcing the RTL. So I have set the search path, the link library, and the target library. Please note the link library contains the SRAM path to the AMD. The target library only points to the conductor. Now we will read in the complete design. So now you could use again I would recommend using the analyze command. So you can say and give a list of files. Now this list of files, since it's Verilog, it can be it not necessarily be in the order of usage. DC will so any Verilog tool usually is able to read out of order Verilog files, so it should not be a big problem. Let's read in this Verilog. So now this is just the analyze step, and it searches for the RTL models in the search path. So it searches in RTL. It finds all these files in the RTL, and it will read them. So there is no syntax error. Otherwise, you will have syntax errors. You will see errors. And as soon as it reads in the RTL, it also loads the DB files, the target library and the link library. Now we will elaborate chip top. Since the module name of the top level design is script up. We want to elaborate it. Let's do that. Now, yesterday we read in one file. Now we have read about 8 to 10 files. So it will start the elaboration process. So the elaboration process will map. It will start inferring hardware and map it to the GTEC components. It will tell you what all memory elements are there, what all flip flops are there. Yesterday we saw the inference for one of the blocks. Now let's see the inference for the case analysis. So we see that this log, it's a good practice to review this log very carefully. So we have learned how to interpret this. Now let's see one of the files where there is a case statement. So it tells that there is a case statement at line 49 in this file, and it interprets. Yeah, let's open this file. So there is a case statement here, and now so there is a function and there is a case statement, and it determines. So this function select 16 will be used somewhere. Yeah, it's used to select something, so it's a function implemented, and this it tells us, DC report tells us that this case statement is both full and parallel. You could see that. So the selection is a hex. The cell is a hex number, and all the 16 possibilities are listed. And since only one can be true at a time, it's both full and parallel. So let's see the report again. So it tells us that in GPR.v, yeah, there's a case statement in GPR.v. It's full and parallel automatically. Here, no synopsis, super case or parallel case pragma is used. So if the pragma is used, it's a user slash something. It will give a user keyword so that it tells you that you as a user are forcing DC to consider the case statement as either full or parallel. If it is not there, it will say no. It is very you should be very careful in your case statements. You should make sure that they are either auto or user. Preferably they should be auto. Second preference is if you cannot make it auto, if you know that yes, only one possibility can occur at one time, and I don't need to write a lengthy code. You could give a synopsis pragma, full case or parallel case, and here it is the user. If it doesn't recognize the case statement as full and parallel, you should very carefully review your code and make sure that this is what you intended. Otherwise, either there will be latches or there will be priority encoder, a slow logic. Right? So I would recommend each and every one of you to, whatever RTL you read, you just very carefully you should review this elaborate report. So one thing you could still do is you can elaborate, and what I'll do is let me remove. So if you want to remove the design, you could do a remove design minus all or minus. So let's see remove design. So the help says that you could remove the designs, and you could also remove the design and library too. So you don't want to remove the libraries. Let the libraries be loaded in. You don't worry about that. You just want to remove the design. So I say remove design minus designs. It will remove all the designs that is read. I will read in the design again. I will elaborate the design, but this time what I'll do, I'll want to store the log file into some file. So I can use the output redirection same as the Unix command into elab.log, and now I see that what elab.log contains. So it contains. It's a very good practice to have separate log files for important commands like elaborate, like compile, or you want to report timing. So it's good to create to store this output into a file so that you could review it at that time or at a later stage. So it's a log of the quality of the synthesis. Okay? So you could review it in a separate file, and Yeah. So it also gives the display outputs, which is kind of don't care for synthesis. So dollar display, dollar time, etc. are simulation constructs. They are used in the RTL. So, but DC ignores them. It's okay. It just gives the display output, but it doesn't affect any synthesis. It doesn't affect the quality of synthesis. Right. So you have to make sure that when you write code, then you should try and see that you should only use a synthesizable code. If you want to use non-synthesizable constructs like dollar display and dollar time, you could do that, but using some macros like ifdef to make sure that they are not read during this. It's a good practice. So yeah. So once you have reviewed the log file of elaborate, you can go, and now you are ready to set the environment conditions, set the design constraints before proceeding to compile. Now, can I do anything more? Can I do any more checking? Yes, I can do a lot of checking. I can do a lot of reporting at this stage itself. Let's see one important checking command called check design. Let's see the help. So check design will give a summary of any warnings related to any input port being untied, not connected, any output port being not connected, any multiple driven things. Some of these warnings are you can ignore depending on the case. Some of these warnings are of a more serious nature. So what we could do is let's run a check design minus summary first to see what is the summary of. So now when we run check design summary, it starts throwing a summary of problems that DC found in the design. These type of checks are called lint checks. Static. So lint checks are static checks run on the code to find out problems that might affect your synthesis. So the check design is a very basic tool from design compiler that gives you a summary of results. A much more sophisticated tool is the Swayam from Atrenta. You will encounter that in your course, maybe in some other course or in the industry. So it's a very famous tool that gives you the power of analyzing your RTL for problems even before going to synthesis. Because in many cases, for at least for bit chips, the synthesis is a very time-consuming effort, and you would like to know the problems that exist before even going to synthesis. It saves a lot of time and effort. So let's see the warnings. So it tells us that there are 15 nets with no load. There is one multi-driver, which I think is a serious problem which should be corrected. Ideally, for cases like multiple drivers or for tri-state drivers, ideally you should instantiate the cells directly, explicitly. You should not let DC map any tri-state logic to a tri-state buffer. It's a good practice not to have any tri-state logic as part of your RTL. It complicates things later in timing analysis. So it's a good practice if you want tri-state or if you want a multiple driven signal, you should use it explicitly in your RTL, not let DC input. It tells that. So it also tells that it tells that in instruction decoder there are 8 ports not connected to anyone. Some of these problems might be benign. You can review and ignore. Many times a designer chooses to leave some ports open or to leave some input port undriven so that he can add design to it later. So these are not big problems. Multi-driven is a big problem, might be a big problem later on. So it gives different kind of warning. So each warning has a group, has a code number. For example, let's see this. Lint30 is a group of so all these warnings have a lint30 code. You could actually check what lint30 means by doing a man on it. So this tells us that this is a terse version of a check design warning message. So lint30 is a code that is used for warning messages reported by check design. Similarly, all the warning error messages inside DC will have some code. You could do a man on that code to know more about it, what it means. So this is a very generic, it doesn't tell much, it's a very generic warning message from check design. Now if you do check design minus without this option, it will start throwing up stuff. It will start now telling, earlier it was telling the summary, now it will start throwing up what exactly is the problem. So it is telling me that in this design, a pin on this module is connected to the logic 0 or logic 1. This is not necessarily a problem, and so it is not very easy to remove all the warnings from here. So you could look out for specific cases. For example, what I'll do here is I'll again I redirect the output of this tech design into a log, and then I'll open this log and I'll search for multiple drivers. Yeah, so we see that in this log file in the non-summary option, it also gives a group of commands which is link to, which means no load, and yeah, so this is the warning which I am looking for. The same net is connected to more than one pin on some module. So these type of problems you should look out for is that when same net is connected to more than one pin, to make sure that your design is correct. And link 33 and goes back to the decision. Let's see what all options it gives. There are specific options like it also tells you whether you have multiple designs. So it also tells you that so see you could also get this kind of information where you have multiple instances. So we discussed in one of the lectures that how do we resolve multiple instances. We see that as part of the compile. We'll use a unify process. So it tells us that design is instantiated some 13 times. So it's good thing to run check design and go through the important whether it gives any errors or warnings. Go through them, correct them if the case may be, and then proceed. So now we read in the design, we did a check design, and you could read more about check design. So there is a man page again, which gives you tells you in detail what each and every option means. Right? There's also a case of no warning. You could do that to first check. So you could prioritize your checking by making sure you list the errors first. Now there are no errors. So you could. It's a very powerful command to check the design. Now we'll start working on the environment conditions. So if we go back to the lecture that discuss environment conditions, there are majorly three kind of environment conditions we have to define. First thing, you have to make sure that operating conditions are defined correctly. So let's see what are the commands are there to specify or report operating conditions. So there is a let's see what operating condition is in place here. So now so we see that we want to see what all operating conditions are available in the library. Obviously, we will use the SwayamPrabha library for this. So we see that there is an operating condition named something is part of this library, and we want to set this operating condition. There will be also an operating condition defined in the memory library. Now, in this case, both of them are different. This is This is 125C. This is 25C. This is 1.2 volt. This is 0.95 volt. This is dangerous. As I mentioned in the last lab session, I do not have the worst case library for SRAM. I'm using a mostly typical library. but in a real design, in a real industry scenario, this should not be the case. You should always use the worst case for all the cells that are in your design, whether it be memory or analog macro, and make sure that the operating conditions are same for each of them and voltage is same. Otherwise, it will give you problems. Synthesis otherwise will not be accurate. So now I want to set the operating condition. Let's set the operating condition and see the help on this. So there is operating condition. So I have command here. So I will not use the max. So you could always read in the min library also, the path library also. You could set the condition. So but it is not needed for synthesis unless and until you are going for some low power synthesis. So what I'll do, since I have just read the max library, I'll just use the max condition. So we can say max and we use the operating condition name, this one. So now it tells we have set the operating condition. It searches, when we say this, it searches for this operating condition in the list of libraries, link libraries. It found this operating condition here and it's set. The operating condition is set. Now this operating condition tells DC what is the temperature, what is the process corner, what is the voltage. But since we only have the worst case library loaded, so anyway that library itself corresponds to a worst case operating condition. Now second thing what we want to do is we want to set the load at the output and some transition or driving cell at the input. So now we want to set the load at the output. So we'll see one of few reporting commands that are very useful. So to see all the inputs in the design, we can type all inputs. And it gives me a list of inputs that are available to us. Since memory bus is a bus type input, so it gives the split in terms of the number of bits. Clock, reset. We can similarly have all outputs. This gives a list of all the outputs available to us. Right, so you could use these things. Now we want to set the load. Now I, as a synthesis engineer, do not know what load to set, but I can always estimate. Nobody has told me, designer has not told me what load to set. But as an engineer, I should be able to work it out. How? By looking at the library. So what I will do is, I will now search the library and see what all buffers are there. So I'll try and get a list of buffers and see and make sure that the outputs of my design are able to drive a load that can be driven by the buffer of the maximum size. Not if not maximum, then very near to maximum. Let's see. Let's first see the list of buffers in the design. So we saw report list command yesterday. Let's see the what all cells are available. So buffers will be starting with either I guess. Oh, it's not B is not there. So yeah, we saw n buffs. So we have n buff 2, n buff 4, n buff 8, n buff 16, n buff 32. So by experience, I could say that okay, X16 or X8 drive strength should be good enough. So this is where experience comes in. X32 is a bit large. So what I'll do, I'll open up the library, models. I should open up the worst case library since this is what I am looking for. I'll search for this buffer, 16 buffer, and I'll see at the output what is the max cap. So max cap is 16. So now if I want that my design output drive should be X16, then I should be able to drive this load. So this, if you see even in the lookup tables, whether it's power or timing, this is the timing lookup table, the index 2 corresponds to the cap, the max cap is 16 here. That means an X16 buffer can drive up to the 16 PF of load. Now, do I want my output load to be this? I'm assuming that it is driving. I'm assuming an X16 capacity on my output. So I can easily do that. I can say that set load. Let's see what set load tells us. So set load tells us there's a min, there's a max. You could read more about it. What is subtract pin load? It adjusts for the pin capacitance from the values and so on, minus pin load or minus wire load. So now we want to, so it also tells us that you can set load on either a list of nets or ports. In this case, we are talking about ports. So we will say set load of, let's say, 16, and we want to set this load of all outputs. Right? So this is the way where I can set load. Right? Now the second thing we want to do, the thing we want to do is we want to set some. So this is telling DC. This is if you do not set the load and transition of the input, you're working in a very idealistic world. So it's always a good practice to estimate the value of the load and transition load at the output and transition at the input, so that your synthesis becomes more accurate. So now let's set some transition values at the input. Now what transition to set? The output we assume a maximum driving capability. Input we'll assume the worst case. We should always assume the worst case. We'll assume that a very weak driver is driving the inputs. So let's assume an X1 driver is driving the inputs. Now let's see what is the maximum transition. Again, we'll open up the library. We'll go to, let's say, we'll search for nbuff. This is nbuff X16. We'll search for nbuff X1. Now let's see what is the is there any max transition at the input. Max transition will come at the input. Max capacitance is usually reserved for the output. There is a max transition of 1.024. I think when we look at the output timing window, output timing lookup table. Let's go here. Yeah. So here we see that 1.024 is indeed the max transition. So now so again the experience comes into picture here. Now I know that the transition of 1 is very bad. 1 ns transition is very bad. Now we'll see that we'll apply a clock of 2 nanoseconds. So we will synthesize the design at 500 MHz. Now when the clock itself is 500 MHz, a 1 nanosecond transition is very bad and will not occur. So we look for some realistic value. So now from experience I know that let's look at buff X2. Now so a buff X1 is a very weak driver. Let's look at what happens in case of buff X2. So let's look at 2. What is the max transition here? So again max transition here is okay. We have characterized it in 1.0. So now what I should do is I should have some kind of guideline. So what the guideline we follow is that in industry is that for technologies like 90, for 65 and beyond, 65, 45 or 28, 20 even, we will limit the max transition numbers to somewhere around 250, 300 PS. A transition of more than 500 PS is very bad, and usually in most of the cases we would want to fix it. So what we could do is again in the same case we can say that let's put our input transition to be let's say 500 PS to begin. You could always change this value later. 500 PS itself is very pessimistic. So there's a command called set input transition. Let's see the help again. It again tells whether it's rise function, fall, min or max, right? So again the argument it expects the list of input ports. Now we should be careful of excluding the clock from the list of input ports. We should not set any input transition on clock. So how do we do that? So if we do not specify any rise or fall, it will assume the same function for both rise and fall. We do something like this. So a list of, if we say all inputs, it will give me a list of all inputs. If I say get ports clock, it will give me a clock. So what I need to do is so all inputs and get ports both return an array which is called a collection inside pickle. So I need to just subtract this from this. The command is called remove from collection. From the collection all inputs, I'll go ahead and remove the clock port. What it gives me is again a list but with clock port action. Now I will use this kind of structure, this kind of coding to set input transition. I say input transition to be, since the time scale is nanosecond, 300 ps means 0.3 on. So a square brace means you are executing a function. So I want to execute this function. Now I have set the input function. Now we set the operating condition, we set the output load, we set the input transition. Do not worry if you are not able, if you are confused about how to choose the values of input transition and output load. Experience will help you as and when you start working on it, you start seeing the lib value, you know, what is bad, what is good. So then what we do is we set the Y-load model. So let's see again. I'm trying to work like a layman. That means I do not know, assuming I do not know what is the command to set and report Y-load model, I can always use help. Now there are so many, you can go a step further and do a Y-load. So there's something called report Y-load. Let's see if there is any Y-load loaded here. So it reports the Y-load for this library which we saw earlier as part of report list. So now see, as soon as we did a report Y-load, since there is an already there is a Y-load automatic Y-load selection available in this library, in the sense that for each module it will apply some Y-load model based on the area. How does it know the area? It doesn't know the area as of now. There's some using some logic. It is just applying some Y-load which is for QA on all the designs, right? Most of the designs. We could choose one of the Y-load models. So let's choose. Since I do not know, so it's always an iterative process. The first time you do synthesis, you will have some area numbers in place and you will have the idea. But since I am synthesizing it for the first time, I do not have any area number with me, so I can choose any Y-load model to start with. So there are so many. So it reported. So it tells me that it chose 2 Y-load models for QA, location chip top, and then for memex it chose this one, because I guess for memory it has the area number, because the memory is a macro, it has a dotlet and it has some area. I'll show you. Let's open the memory list and let's go to the area. So it has. So okay. So this memory library has Y-load models. This is not normal. Usually analog macros and memory list will not have area. So it has some area which is about 119 K microns. It has this area. So based on some distance, it has some area numbers available. It chose one of the Y-load models. Now I don't want this Y-load model, so I can set my own set Y-load model. So this is the set Y-load command or set Y-load mode command will set mode. So let's start with something. Sometimes so now this single command called set Y-load, which is available to us, it will set all the things for us. We say mode, we say let's choose stop to be reverse case. Let's choose the mode name. Let's choose mode top. Then let's choose the library to be. Let me list the library first. set value. And now we could change. We could select the model name. So let's choose this 20. Let's choose 28,000 itself for the complete design. If I want to do that, and let's do it on current design. Okay, this command is obsolete, so we have to use another command. This command is obsolete. So set Y-load model. Okay, now it has split, so we set Y-load model minus name minus. Okay, the library name is optional, so let's leave it. And we will. So this command set Y-load model minus name. Now let's report the Y-load model. What does it say? So it tells us that the design flip-top has this Y-load model set now. So we set it. And for design instruction decoder, it is choosing for QA. Just because I guess since it might have some cells instantiated, so it is choosing this. Let's set the Y-load model, Y-load mode also to top. Yeah. So now this area, this area number, this comes from the Y-load. Let's look at the Let's look at the list. Let's look at the Y-load. So we set this one. So these the area numbers and the slope and cap and resistance value comes from here. So now the Y-load is set. So usually in the lower technologies you don't have this kind of a area based Y-load. Usually it's a custom Y-load, that is each design you will have some Y-load and you will apply that value. So that depends on what kind of technology library you are using. You can always do some experiment. So to know whether you selected a good Y-load model or a bad Y-load model, you will only know after the design goes to layout. So if your estimated numbers, if your estimated net delays, when you go to layout, if they blow up a lot, that means your design was wrong. But if the timing remains good even after the layout, if the timing of the post layout is very similar to the pre-layout, very similar to the estimated values, you selected a good Y-load model. Now, as technology goes on shrinking, the Y-load models do not provide a good estimate. So we have other methodologies that are replacing Y-load models. I'll discuss that some of those in other lectures, upcoming lectures. But don't worry too much about which Y-load model to select. You could always start with some values. Right? Now we've chosen Y-load model, operating conditions, transition, and loads. Now let's also look at a command called report port. So report port will tell you what did you actually do. So it tells us that the port input, the fill load is 0, the Y load is 0. We set the capacitance for. So we set for the output ports, we have set the load to be 16. It shows us there. I guess there's also a command called report port minus verbose. Yeah. So there's a report port minus verbose. Verbose means it will give more details. Let's see this. Now it's also started to give us something. So whatever we set with respect to ports is available to us in report port command. For example, we have set the transition to be 0.3. So here it's reporting that each of these input ports have a 300 PS transition. So you could use this command to verify whatever you have applied is being applied correctly by DC or not. Now we have to set the design constraints before going to compile. So design constraints, first we have to specify the clock. How do we specify clock? We use the create clock command. So we know that the port is called clock. We saw that there's a port called clock. We'll create a clock on this using this command. So create clock minus name clock. So this name can be anything. We are creating a 500 megahertz clock on the port clock. So the clock name and the port name, they are both same. Please note the distinction between clock name and port name. This is port name, which is physical port of the design. This is a name, just a name. It could be anything. So I do this. So the clock is created. 1 means the status is successful. You could also do a report clock and see what all clocks are created in a design. So this is the clock. Waveform means that at 0 there is a rise edge, at 1 there is a fall edge. So if you do not specify anything, so create clock has not many options. If you do not specify any waveform value, any waveform list, then DC will assume that it's a 50% duty cycle. Right? So 0 rise, 1 fall, total period of 2ns 500 megahertz. We created the clock. Now we'll have to create some input delays and output delays. Let's take some value. So typically for such a fast clock, 500 megahertz clock, the input is the clock frequency is 2ns. Let's say I reserve 1 ns out of this to all the inputs. So I give 1 ns as input delay. How do I give? I use set input delay. I do a -n. So there are so many options. I'll do the most standard thing. I'll say with respect to what clock, with respect to the clock, since the name is clock. I give a value of 1 ns. Please note a set input delay without minus clock option. It will work, but doesn't make sense. So you have to make sure that always you give a related clock for set input delay. In this design, we only have 1 clock, so we will define with respect to this. There is a concept called virtual clock, which I discussed earlier. You will see lot more of virtual clocks in unit 5. And I do this on all the inputs except clock. So the clock input, since a clock is coming there, a pre-running clock is coming there, does not need an input delay. So again, I will use this construct remove from collection, and from list of all inputs, I will remove clock. So send input delay is done. Again, I will do the same value for output delay. I am giving 1 ns to the output. This is pretty simple. Again, we choose 1 ns, the reference clock, and we choose to do this on all the outputs. This is a very basic of the design constraint that we applied. We specified the clock, we specified the input delays and output delays. Now you are ready for synthesis. You have to do this for if your design contains multiple clocks. You have to define all those clocks. You will see the case. We will probably see one of the examples where you have multiple clocks in the design. How to do that? Because then the clock relationship becomes also important. It's a very important thing. Here that doesn't make a difference because there's only single clock. In a multiple clock design, it may happen that few of the inputs work on one of the clock domain, other inputs work on another clock domain. So the input output delay commands with respect to same. You have to choose the correct clock. So this now we have defined. Now we are ready for synthesis. Again, we'll do a report port minus verbose and see that this is the key attributes. Extra number of points. There would be a field where So it tells us that there is an input delay defined on input port this with respect to this clock. Right. So we saw the input delay. There would also be an output delay table. So there is a transition table. There is an output delay table. So output delay, input delay have option of rise, fall, max and min. For synthesis, usually you will always be worried about the max value. So if you don't specify anything, it will assume the same value for both rise and fall maximum, right? So you could change the values for if the input is rising or output is rising or output is falling. So there's a lot of configurability, but for synthesis, this is not very important. We are only worried about we want to reserve some time. We want to give some time to the outside world on inputs and outputs. So we specify the input delay without the rise and fall. It's enough for synthesis. For synthesis, the max value is important. We are talking about the worst case, but the min value becomes very important for static timing analysis. So when we talk about synthesis, all the values we give, the input delay, the output delay, we choose the worst case average, they are all worst case stuff, since we are worried about the performance. But when we go to unit 5, when we study unit 5, the static timing analysis, the min delays also become important. They also start playing a factor. So all these commands which are simple in DC, like input delay, set operating condition, and so on, now will become a lot more complex when we'll come to the prime time, when we'll come to the static timing analysis. So this forms the synthesis. These are called timing constraints, creating clocks, input delays, output delays. They are simpler for synthesis, but they might become lot more complex for static timing analysis. Just keep that in mind. Now we have everything defined. Now I'll just now see what all options does compile-etra give me. So there are two commands, compile and compile-etra. Since compile-etra is available to us, I'll start using that. Compile-etra is much more sophisticated than compile. So let's see what all options should I give in compile-etra to start with. To start with, I want to do a simple compile without scan and without clock gating. We'll study more about clock gating later. So to start with, I want to do a simple compile. So what I'll do is I'll choose the simple options. No boundary optimization. We'll come to this. I choose no sequential output inversion. These are all sophisticated techniques, but I don't want to do any of that. So I just do two simple things. Since scan, if I give scan, it will do scan. If I do not give minus scan, it will assume it's a non-scan thing. So no is the negative option. So I do not want any boundary optimization. I do not want any sequential output inversion, and I do not want any other stuff. So I can do this. However, I can say no design rule to not fix design rule in this pass, but I can choose only design rule. It will fix only design rule and don't fix the timing. Whatever, I can do that, but this is the most simplest of the command, compile-etra minus no boundary optimization minus no sequential output inversion. So this will synthesize the design without scan, without clock gating in place. It will not enable boundary optimization, and we'll read more about this, no sequential output inversion. So I'll just press enter, and now it will start compiling the design. Let's see the messages. So it loaded stuff. It loaded the designer component. It loaded the now it starts. It is ungrouping some hierarchy before pass one. I give okay. Okay. Fine. So now it will do a pass one. It has again it will do a multiple iteration thing. So now it gives the elapsed time, the area. So now you see it is working on delay optimization phase, then sequential optimization. Again, it will do multiple iterations and it will do a design rule fixing, as we saw. You could go back to the slides and make sure that whatever is in the theory is actually appearing here. Then it will. You see that it's working on the area recovery phase. There is a worst negative slack of something. It means that there is a timing violation here. So now the synthesis is complete, right? So you see that there is it completed in 1 minute or so. This is the area. So during the delay optimization phase, it saw the timing violation. This is the timing violation, WNS. This is the total cost, the total negative slack of all the paths that are violating. We'll see more of that later. And So we see that during different iterations here, actually the area is starting to increase. From this value to this value, it increases a bit because it is doing design rule fixing. During design rule fixing, it is maybe size of the drivers, it will add more buffers and also area will increase. During delay optimization phase, it will the WNS worst case violation will decrease and also the total negative slack will decrease. This is where it fixes the timing. There will be an area recovery phase where you see there will be some area recovery phase. Here the area is reducing. So we see that we actually see the priorities taking place here, right? So it can recover area, but it has the lowest priority, and it will first fix. If you do a delay optimization, it will fix design rules. By fixing design rules, it will make sure it does not. So by fixing timing, it will make sure it does not violate design rules. Area comes last, and so on. This last one is the design rule cost. So we saw that we see that earlier there was some cost. That means there was some violation, there was some problem. Here it becomes 0. That means it's clean. So this is the compile process. Now what we can do is we can write. We can choose to write out the netlist. We tell basically that okay, give me a netlist or format dialog. Hierarchy means give me all the modules, not just the top design, and the output file. That's write chip.v. So now it is writing it wrote a netlist for me, right? It gives some warnings. You could read more about it. Let's see. It tells that there are some unconnected nets which are named as this as prefix. Let's see chip.v. So now it gave us different modules. So usually the last one would be the top level. So this is the last module in this list in this file is chip top. Again we see that let's look for the different modules. So again there are general purpose registers, there's a SRAM is instantiated. The names are a bit odd. I will tell you how to fix these names later. We see that there are some okay, it looks like it ungroups something. Let me see. So general purpose registers, okay. Yeah. So the number of modules we see here is much less than the number of modules we found in the article. This is the result of ungrouping. So it gave a warning also here that it is ungrouping hierarchy. Let me see. So this warning is it tells us that because the specified hierarchy is automatically ungrouped, and we can so there is a variable which controls this. So again by doing man and help you could gather information. So now there is this variable which is set to true. So I set it to false because I do not want to ungroup all. Usually you do not want to ungroup everything in your or all the small design in your all the small blocks in your design. You do not want to ungroup them for various reasons. You might have problems in formality and all that. So you could whatever you want to choose, you can use this variable to control. So if you set this to false and then again do a compile, with same option. So every time do a compile or compile algebra, it will start from GTech again unless and until you are doing an incremental option. So if you do not tell incremental, it will start again, and now it doesn't give me warnings. It doesn't tell me it's ungrouping because I set the variable to false, right? So this is how you control the compile algebra by default will ungroup small blocks, but this is the way you can choose not to. We will see that the area might be slightly bigger than before, only slight since we chose to keep the hierarchy. So module hierarchies will limit the amount of optimization that can happen. We saw that in the lecture slide because it creates some boundaries and DC will not optimize across boundaries. We have also set boundary optimization to false. We said no boundary optimization. So again that will also lead us to increase. So So many times it's a trade-off whether you want the lowest area or you want. There will be many tools that will work on this netlist. For STA you will work on this netlist. For common verification you will work on this netlist. So we'll also have to think about that. How do we make that process smooth? So many times we choose to not encrypt the design. Many times we choose to switch off the boundary optimization just because we want to make our job easier later in the flow, right? So again we see that this is done. Again I'll write out the netlist. I'll overwrite that file. I'll again open this file and see now that now there are how many modules are there. Okay, looks like it was only I have to fix something, but that's all right. Let's look more into this in the next section. So in the next section, I'll focus on again. I'll do one more compile and I'll show you the netlist without ungrouping. I have to check that there were some errors. I have to check that if indeed can be all the analysis. So let's in the next session we'll also see now our design is synthesized. Now we'll focus on how to report various metrics. How do we report area? How do we see what timing is violated? How do we fix that? We'll look at different timing groups, input to register path, register to register path, register to output path, and probably we'll also look at the clock groups. Thank you.